So welcome, we will look at how we can build binary counters from JK flip-flops and how we can make them count modulo 9. The JK flip-flop we're considering has this internal logical diagram. So we're looking at a positive edge triggered JK flip-flop. And the function table can be shown to be as shown on the screen, where the stars mean arbitrary input. So we use this diagram for this JK flip-flop, and we have the circle on the K because of we can see that we have a slash K in the function table. So, and we have a clear and a preset, and they are negated as well as the circles show. And this is also the case for the function table. Fine. Now we want to look at the timing diagram when using a clock. So first we look at the simple JK flip-flop, and we set the negated preset and negated clear input to 1, and then we look at a clock pulse, and it's positive triggered. So we're looking at when the clock goes from 0 to 1, what happens with the Q output of this JK flip-flop. Well, it gets triggered whenever the clock goes from 0 to 1, so QA toggles whenever the clock goes up. So we get this output. But what happens if we have two JK flip-flops and we connect them like this? So we take the negated output of the first one and use as a clock pulse for the second one. So this means, because it's positive triggered, that the negated Q has to go from 0 to 1. So actually the second flip-flop gets triggered when QA goes from 1 to 0. So it's actually going to be some kind of negative triggered flip-flop, because we use the negated output. So when QA goes from 1 to 0, the second flip-flop toggles. So we get this kind of output. And we can continue this with one more flip-flop and the same connection. So we take the negated output and use a clock pulse. So whenever QB goes from 1 to 0, the third one will toggle. So we get this output. And then we may have a fourth flip-flop connected in the same manner, and we get this result. And this is actually a binary counter with 4 digits, binary digits. So we can see QA is the least significant digit and QD is the most significant digit. And then we get the numbers 0 through 15, or as binary numbers 0, 0, 0, 0 through 1, 1, 1, 1. Fine. But what if we want the counter not to count modulo 16, but modulo something else? Let's say 9. So then we can use the clear inputs of the flip-flops. So we take and connect some of the outputs and negated outputs into a NAND gate. And what happens then when we use the output for the NAND gates for the negated clear inputs? While the flip-flops get cleared, so this means that the Q's will be set to 0. This happens exactly when the output of the NAND gate is 0. Okay, this means that before negations the AND gate will be 1, so all the inputs should be 1. So this means that QA and QD is 1 and QB and QC is 0. And this is exactly the number 9 when considered as a binary number. 1, 0, 0, 1. So let's see what happens. We can start to do the first part of the timing diagram, and we see that as long as we don't get this QA and QD equal to 1 and QB and QC equal to 0, then the negated clear inputs will be 1, so we get the same results as earlier. What happens now when we go one further and we get this result? Well, right after we get into this state, all the flip-flops will get cleared. So what happens is that we very shortly after the clock pulse will get all the Q's to be 0. And then we can start to count again. So we will get this timing diagram that counts modulo 9. Of course, you have to be a little bit careful. This is a asynchronous counter, so you have to make sure that you don't get cleared falsely on the way, because the Q's don't change simultaneously. But this won't happen in this case, because the QA changes before the QB and before the QC, before the QD. So, thank you.